Today we have our document, and I wanted to go through a couple things before we start our group. So the first thing is about on the general channel. I have highlighted that Sahej is actually due because it's already week 8. Okay, so every even week is another deadline. Okay, so I hope you guys will spend between today and next Thursday updating your slides for sprint 3. So if you go to the pins in the project channel, right, you will see the project sprint 3. You can just copy the whatever new slides you see and then put it here. So you can see rough timeline week 8. Your availability is very low for NUS students, but they're all taking midterms. That's why we have a pretty empty classroom today. And online we only have 8 people. So it's a little bit more. So you just need to fill out the things that are new. So there aren't that many things that are new here. These are all slides. Okay. So mostly what you can do is just add a little bit more of the development that you have done. Since again, this is second season. Okay. So by the end of week 8, tomorrow, and week 9, so Thursday, try to think about the rest of your development. Okay. After that, again, it should become even more busy for NUS students. Around 9 or 10. You actually have very few little time left in the project. That means you're doing your analysis, rounding up the projects, getting ready for communicating the project with the community. Okay. So the other part of that is that in this course, as we've said before, the general problem that we have will be that at the end of the course, we have this project presentation called STEPS. STEPS stands for SOC Term Project Showcase. And there is a version of that every semester. So you can take a look at the one that is on for the 26th. That was last semester. Okay. And then you can look at what happens in the show. Okay. In fact, my last course, which an NLP course, we also participate in steps in some of it here, Indra and Song and others. So you can see the project statement. Okay, then this is a good way to go through this. So when you look at this, you'll see what is required. So I'm just going to dump this into Slack so that you can see this. So go to that. You can see the projects that are 4th year students did for, well, mostly 4th year students did for their natural language processing class. So, for example, on emojis, this one, you go to the project, you see that there is an abstract, okay, for a number of project mentors, and there's a poster that they had to create. It's not on this one, but there are other ones that haven't had. Okay. And, that is what we want to prepare, okay, for this course. So fine. So they have to prepare posters is saying that you would actually prepare in your projects to be printed at the SOC Technical Service Desk, which is on level 1. And then you're trying to advertise to other people about your project. So that's what's going to happen over the next couple of weeks, because week 13, now it's week 8, right? So in 5 weeks, Wednesday night, that means the night before this class, we will be in the calm, free, multi-purpose space, along with many other courses. Usually there's a game development course, another couple of our game systems analytics people who present. There are prizes, so usually at least one person from this class will get usually I think $75 or $150 richer because it's a popular. So please put that in your schedule. All right. So what I will be doing is going to our sheet. I would be taking all the project groups. So there's 4 people in 1, 3 people in group 2 and 3. Okay, then registering your email addresses and your names with your project. Right. So the project, I go to our Slack. I look at team 2. Whatever you have on the title page of your project in sprint free is what I'm going to put there. Okay, but you can edit it. Okay? It's not to say it's this. Okay? So I hope that helps you get an idea of what will happen. So then you'll see something like what you see for last semester, where you see all the different projects, and then how they're configured, like who's in which project. Here, see place the project page, URL, portion of video, have one, post the image which is required to create a poster, and I use any other. So that will be coming over the next month. So please be ready to do that. It's fine if you don't have all the details, but it's something there. Okay, with that, it is time for Kahoot. Zaidan, I know you're online. Do you have any updates about the code that?
Sorry, Professor. Me?
Yeah, Zaidan, do you have any updates that you want to give about the article preparation?
But no, nothing special. Thank you.
Okay,
Okay.
no worries. Yeah, I just wanted to make sure you had a chance.
Okay.
As I told you last week, I tell myself, Jisong, and 1 or 2 other people going to be taking outputs of our class notes and scribes and trying to put together a more longer course materials to update our CS6101 retrieval. All right, so we're going to start with Kahoot. So please join our Kahoot. So, Sahej prepared the quiz, but he's not able to run it, so he has to take over. So I'll narrate in RAG fusion. Which method is used to merge rankings? reciprocal rank region. You go back, that's the idea that you have reciprocal ranks. Top one counts as one, the second most rank counts as 1/2, all the way, let's say to 20, which counts as 1/20. We integrate these over several different outputs, and then you can get a composite. So Neuros in first place, CM second place, and KK's God. The corrective brag or prag introduces which he just gives it away, right? Because the corrective here, no, these other ones have corrective, so we got 11 people guessing the right answer. So we'll go on to next. And there are retains placed in the top, but data is coming in second place. And we'll go to our third question of 6. Which of the following models focuses on aligning retriever and generator training? It's very good for the majority of us. I guess Sahej made it very easy to do the training. So consider yourselves well trained. I'm sure you won't make that mistake again for the 2 and the 3 who pulled the other ones. Maybe match them. Okay, so there are retains for lead. KK's God is upended Zai section. Okay, 4 out of 6. In that model, the retriever is optimized by optimizing backwards. We belong to the very last one. There's a passive retrieval score generated by the retriever. The LLM supervision score for generating the output. And these will sort of have to match with each other in order to build a more complete model. Okay, that's done by scale divergence. So that we're still on top, still not to be undershadowed, it's not very far behind this and data. Okay. So 4 out of 6, 2 more questions. Again, in the same model, how is barely finished narrating that. So we have triangle as the right answer, where the LLM learns to filter the irrelevant documents by cognitive training. That was pretty hard. Ada has upended Neura, and now it's first place. TZ is second. Neura hanging in there on first place. Come to the very last question. Hey, this is it, guys. Which augmentation strategy interleaves retrieval with reasoning step? So yeah, you have interleaves retrieval, right? So it's IR absolutely. So congratulations to Ada in first place. TZ in second. Nothing except for infamous reputation on YouTube. So congratulations everyone. Okay, and with that, we are going to go ahead and do our lectures. So if you have two long lectures that have 8 to 10 lines, which is a good sign, you might actually get out and write it. Stop always interjecting. So we'll have Jonathan and go ahead and pick John.
So we're going to talk about the document submission today. This is how to use basically embedding in other model and the text and the other information in the visuals, the table layout, and as well. So starting with the introductions, we talk about meaning of words here, with basic knowledge and also vector syntax and embeddings. Well, the meaning of words in linguistic terms actually within the mass and sense here, which means the meaning component can have a multiple sense for the same words here. You can see a simple word amount, it can be a small both as possible with added price we have here, right? So it's actually in the kind of mixed terms here, the synonyms have the same meaning here, similar meaning I would say, because the argument here is actually there's no actually the synonyms for the end language here over the hundreds of years evolutions here. We intend to see both of those cannot be done with words along the time as well. Of course, it's also that changes. So then actually, how do we define the word here, right? So another actually mentioned here by the usage here, right? So so how to use the define the meaning by the words here is actually like what's the Wittgenstein has said in the philosophic investigations here, the meaning of words is actually in this usage of the language, which means if A and B have the almost identical environment, then we feel that yes, no, this is how we define the meaning of the words. Okay. And this is very much inspiration for us to go to the embeddings here. So embedding is actually looking at the words happening around this in the sentence training data. So we define the meaning. I show this slide actually very interesting findings from this paper. It's talking about actually we see the embeddings over the years. The only words get changed. It's dynamic. So I mean, we can talk about the case here at the very beginning. It's actually a little bit of negative. I see in such it's only the word scale means it's something associated with negative feelings here. In 1950, it's getting a bit different, possibly. Then in 1990s, I'm negative. Alright, so say for the other words here, what sort of custom means 100 years ago or 50 years or early, then it's actually getting changed over the time as well. Now this is actually highlighting the nature of the human language evolution over the years, and also this meaning is actually context as well how you said get changed. So there, I mean, the two. This is a classic paper we talked about from the very past here in terms of what representation in vector space here. Stable and also steam graph here. I think it's all proposed by the same paper. It's just one proposed the central word, and another one trying to predict the surrounding words here. Then this is actually the highlighting the solutions of the whole eras over the next embeddings here. It's starting from very beginning part of the times here we learn about the old time here we talk about mega words idea basically uses the count of the words here. And actually IDF introduce another way is that if the words appear in two often in the document, which means that word is not so representative. So it's inverse of the document frequency here as well. And the same thing brand here. So this is the first era. The second era comes in is actually using the model, that's what I said earlier, right? So the Qianbo model or speed model to predict the either surrounding world or central world. It's kind of forming that is the definition here. So which means the word actually the meaning and the surrounding is sense. And actually that itself is a limitation for sure, but this is itself is actually a big improvement over the first era here. The group is promoting the global view of that additional stuff. Then the third era comes to especially the paper of the people introduce the dynamic kind of a representation by using the bidirectional. It's a word model, SPM, or some other models here that use the amount of weight to train that. So that means a word the meaning of words dynamic based on the context as well. This is exactly what is used in the human language today. And along the way, there's a bird model, very important model coming out. And to introduce the bidirectional model and transformation model, transformer model used as well. So to highlighting this evolution CSS become like a much more better performance than before. Then coming with the first era here, this is actually the cases when the third era here, they have limitations. It cannot fit generally over the domains and topics here and tasks as well. So coming with fourth era, they're trying to generate the universal kind of embedding models for the general purpose. And that's actually have a lot of developments here. So that's this is what is here. Then along the same path here, there's also sentences representations here, because the word and sentences are two basic units of the whole documentations here. There's a lot of ways to have that developments. Right. So there's basically two different approach for this. One is actually supervised approach here, which is actually to try to obtain the sentence representation from a pre-trained model. And then there's two methods of that for the natural language inference here, which is a supervised model, which is the representation of the first token of the encoder, or the representation of the first generated of decoder, and also the meaning of the representation from the encoder. So then also people try the unsupervised version as well, and trying to see that whether they can generate much better sentence representations here. So this case, using the contrast deep learning technologies, optimize the sentence representations here. And one actually interesting while reading from the paper is actually trying to learn from the image computer vision, which is augmentation, to generate a large number of good quality training data here. And we found out actually it doesn't work here. Because in the computer vision, why you know that augmentation actually you augment the picture a little bit of here and there, you get a very different picture, but the meaning does not change. But in the in these areas here, we found actually you can take a little bit of word, the full meaning change drastically. So that doesn't really work well. So actually, then actually they try a different approach here. What I see actually very interesting finding is actually they use dropouts as kind of a dropout is very common certainly in the deep learning neural network here. We use dropout and that kind of try to generate the kind of automated the training the model as well. And that performance leads to the better sentence representation here. Yeah. There's a lot of alone here, but that's actually my part of the overall the text embedding and generation. Some reference papers also use. So in class we will talk about representation for image and visual identity.
Okay, let's thank our speaker first. This one we have a little list come up. Maybe we can go through some of the different parts so that we're clear. So when we first started this lecture, weeks ago, we were talking about how do we come up with embedding? And Jonathan just roughly went over all the parts. You guys have any questions about all the technologies that we very quickly went through? Do we understand, let's say, what are the 4 eras of text embedding and why it's required? So what are a bag of words, TF-IDF? Everyone is familiar with that? The idea that we have these 2 parts, especially representing things as just words with its neighbors, and then looking at the frequency of words out there, words are with action. That gives you a score, but it doesn't tell you the semantics, right? It just tells you how words are. Okay. When we get to the second era of love for the past tense, what's the key summary we can think about this part? Jonathan went over it from here, right? This one on this part, right? Words are defined by their components, right? So that's the whole point of saying something like what we see in a CBAL and skipgram. These are 2 versions of word to men. Okay, they basically say, okay, if I want to know what this word is, then I have to look at the words previous to this word and the words after. So if you see many thousands of cases of a single word, that the 2 words before the 2 words afterwards, maybe they gives you some idea of what those words are. And similarly, the other way around. If you're looking at a single word and you try to define it by what could be words around it, do prediction the other way. Okay. How about for this? Okay. Verb, sentence, verb, novel, GPT, D5. What's the defining feature of that? Anyone? Dynamic. Okay, it has a bit to do with, the fact that we are now incorporating models that are just more context specific. So if you know BERT, it relies on the LSTM, short-term memory model, going both in the forward direction and backward direction. And Elmo, that's Elmo. BERT goes in one. Elmo does this but with 2 layers. Okay, and later we go to a transformer. Okay, so these are now getting more sophisticated for this. So if you think about this part, it's getting more sophisticated models, like said, more dynamic. Okay, and then we have ones over here. How about these? Okay. Like it says here, universal text embedding. What do we mean by universal? Many times we're thinking of something like multilingual. Okay, so if you solve it for just one language, you use multiple languages and embed them into the same space, and you get good outcomes with that. Okay, this is why when we talk about scaling laws, that a lot of things like GPT can do translation, even though they weren't explicitly trained for that. Just seen enough multilingual data that they can start to do these processes, right? Because they've seen data in Spanish, Chinese, English, and then they can they see context intermixed, and then they can guess. Okay, so this is why we say universal text embeddings that accounts for that, and that also means that these text embeddings are universal not just for languages but for modalities as well. You train a language model, foundation model with images, and start to caption texts, right? Caption images to say, oh, this is a lecture room and there's a TV screens hanging from the ceiling. So, okay, because it's seen TVs, knows what they look like, they got the captions and everything. Okay, so when we go to sentence representation, these were embeddings for single words, right? And then we can do very simple things with sentences as well. So there are lots of cases of this. Some of them we've had visitors coming from before. So Thomas Nikolov from Quebec and was also responsible for state pop vectors. He was here last year and he'll point back to SSC at some point, I think. And some of the other ones like sentence birth, that's done by our friends for Rich, raised about shop, sure. All right, so with that, do you guys have any questions? There's also a nice discussion question in the general channel. That I think our discussion leader is responsible for. So as you're going through and listening to Nicholas, maybe you can also give some off there, okay? So let's kind of get started.
So I'm first going to compare to representation for images. Okay, so let's start with something very simple. Okay, so what you'll see here is very simple as an image of a cat, right? However, what the computer sees is probably just a bunch of numbers. So it's like probably some vector with some numbers. And each of these numbers represents some pixel that so our image is basically comprised of many pixels and together it's visually seen on the screen. Okay, so I'm going through some basics because most of our like your image encoders, they will try and manipulate these user values into something that matches with other images. So basically, our interest can be classified to three different types. First, will be black and white. So it's simple. They use the dividing system to represent colors. So 0 represent black, then 1 represents the color white. Then for grayscale, it's the same, but now range or represent different shades of gray. So it can be from range 0 to 25, so it's 8 bits. And then lastly, color. So there are many different color models. So like RGB, CMYK, and PSP. But which is the name RGB is the most common model. So each of the red group has technical values of those like and each of these values has technically the same of the color. So this takes up around 16 million colors. So let's bring us back to our image. So let's give an example. So we have this so yeah, so here will be some brown and then for here will be this for so okay, seems pretty basic. So why not just use this fixed representation as our embedding and then better? Okay, well, it's not that simple, okay, because we know that the values have no semantic meaning, so there's really no point in testing as our embedding. So another issue is that when we use a model to do feature extraction, there's nothing really telling it that this is linked to the text in CAN, for instance. Right? It just tells you the features of this CAN. And then when you do querying, so let's say keep a query say, I want to know what a CAN is like. So how can we connect the word CAN to this? So that is what I'm trying. So this brings us on to DRMs. So it's a visual language model. So they simply use the try and use text and images and see how we can interact with one another. So there are family of DRMs, and what we're interested in is the contrastive one, because what it does is the image and then text embedded, and then the similar they want to push it together. So what we want to push is try to make it as similar as possible, and very different but try to push it. So what does contrastive DRM do? So it's not just to align images text with joint feature space. And it consists of 3 key elements. So first is your image encoder, second is your text encoder, and third is some strategy to fuse the information of these 2 elements. So this brings us on to FLIP. So this is contrastive language image retraining, and it is built by OpenAI, and it's actually very good for zero shot prediction. So what it does is, well, why is it very good? Zero shot prediction is because it's able to just encode the image and then with these certain labels that you want to see, just the image, encode the text, encode it, and then you'll find the best possible value. Okay. So I will be going through how it's trained, and by knowing how it's trained, you all understand how it works. Okay, so let's begin with the data set. Okay, so it's trained on image transparency. So, for example, it will be, for example, you show a cat, and you pair with a label cat, and you show a car, you pair with a label car. So, the goal of this is to train its text and image encoders such that matching pairs are close together in the shared vector space. So we can let the TI to have embedding for next I and then I change embedding for industry. Then can form all possible pairs of text image embedding, and then can form basically positive pairs and negative pairs. So if we look at this, positive pairs are this diagonal one here. Then everything else is all negative pairs. Okay, so with these pairings, we can just use the very simple cosine similarity, and then this gives us the simple score for the positive pairs and the negative pairs. Okay, so now I think everything is pretty more clear. So now what we want to do is run our encoders to ensure that similarity score for positive pairs is as large as possible. So we're going to maximize this score, but also for negative pairs, we're going to minimize this. Okay, so what it basically does is train their encoders to encode the text and image for positive pairs to be exposed together as possible. And so you will definitely need a loss function. So what they use is equivalency. Okay. So basically this function here, or sorry, this formula here, is just taking the average sum of the exponent of the positive pair, which is the numerator. Then afterwards, it's just the denominator is just sum of the significant score for the positive pair plus for the negative pairs of the same. Okay, so it actually does this twice. So once for image to text, the other is for text to image. Then you take the average and then loss score. So before I continue, let me draw a visualization of what it does. Essentially, we will have some space here. Okay, then for instance, we will take this green one here, insert this our positive pair, so basically somewhere here and so and then this red dot here is a probably a negative pair. So click by us that when you trade, you want to push this red one further away. While we'll try to make the green ones come closer to each other. So we'll come closer to each other. So when you were to use an image and then afterwards embed it. So say after training, it will be probably something here. So we know that when we do retrieve documents, we can retrieve everything here by this one. This will all be related. Whether the image or text will all be related. So this is what it does. So seems pretty cool and seems pretty powerful. But there are essentially some issues to this. So first is that it has a bias for first object. So what do I mean by this? So essentially, let's say your query is one image. I want to know more about like dogs walking, humans walking their head. So most likely, the first word, which is human, will be more accurate than the second word, retrieval accuracy. So why is this so? Because the people dive deep and hypothesize some things, and also did some tests and then take a look at the hypothesis. So what is this hypothesis? So basically, the training set that is trained on has this biasness whereby large integers are the reference more to the first word in the text labeling. So for example, if our image is like for instance a classroom book, then the tag will most likely be like a group of in classroom. So people will be also this picture assets. Yeah. And also there could be also biasness on text and image encoders. So what I mean by this is that let's say for instance there's a large image of let's say people with suits. Okay, and then our tag is CEO. So obviously take a moment to click for that image is to here. But let's say the image has mostly comprised of a particular gender, male or female doesn't matter. Then there's also this tendency and bias to also associate CEO with this particular gender. So if you were to query and say CEO in the future, we might get more of this particular gender's text or images stuff, and vice versa. And also in category, you also cannot provide high-level descriptions of the given. So it's not good for force it is good captioning. So the click is not very good. So maybe just don't work with images. Maybe just completely work with text, and that's 100% so. So the way to do this is to do image tree. Afterwards, scan the captions, and then after that, use our regular text input. So if any generate the captions, then edit with whatever you want to use. So there are many ways to generate captions. The first is to use OCR, which is optical character recognition. So it just finds like patterns in the image, and then it release them to letters so that your formula corresponds. But however, this is definitely not very good if our images have no word there. So this is where the second point comes in, which is to use captioning, which are the so I'll be going through one this captioning model, which is called WING.NUS. It's a single shot memory augmented image captioning model, and I'll be going through this entire series for you step by step. So first, what it does is you will do a retrieve and filter. So WING.NUS contains or has a large textual memory. It's a CC6101 data set, and we will use a quick chain clip to retrieve the top and most relevant description. So basically, this is the image, then also the various text, and afterwards gets the most relevant ones as our descriptions. Then afterwards, to reduce noise from S informative words, it uses a text graph parser which used to form subject predicate object terms. So from my understanding, what this is, it just forms relationships between words. So for instance, an example, Mary loves animals, so Mary is our subject, loves is our predicate, and then our object is animal. So once we done that first phase, the second phase is to merge it. So using sentence bird and process similarity with some threshold, we can merge words into sentences. So you can see here the H. So maybe teddy bears and bears are the same, so they'll be in this position. And then possibly rock and ledge similar as well, so they'll be in this. I also do take note that the relation is still over here through this dotted connection. So this, the relation space is between. Then afterwards, the filter rate. So this type will make the assumption that concepts related to the images will appear more. So what does it mean by this? So let's say we have some image of NUS, for instance. So it assumes that the text that we retrieve from the first set will split or mainly contain lower NUS. So that's the assumption that's trying to make. So thus it will complete the frequency score between each cluster. Okay, go there and then discard those below a certain threshold. Okay, so after filtering out, so just based on this will be filtered out and this will be filtered out. So we will then take the most relevant one. So that's why you provide key concepts. So each cluster they can invert. So users click again to get the most relevant one. So same thing for users process energy to get best word possible. So then afterwards, once we get all this words for each cluster, key concept, they just pass it to our receiver to generate the sentence. So this order keywords just means that is the ordering of the triggers because it follows the same ordering as the triggers. Okay, so seems like that's good. Okay, but there's actually some issue with this. Okay, is actually issued with Seabird. So what Seabird does when it generates sentences is that one of three things. It will first copy, which keeps the current word. It will either replace, which is to replace another word, and also lastly to insert a word for here. So issue is actually with last two, which is placement and insertion. Uses words which are drawn from probability by the pre-trained language model by Seabird. So therefore, this ensures fluency of the sentence, but it doesn't consider actual visual text conditions. So the captioning that provides may sound fluent, but it may not be related to this image. So how does authors solve this? First, it solves it by using memory augmented visual related fusion. Okay, so it seems very simple. P fusion equals to alpha PRM plus beta PRT plus gamma. Just addition of three numbers, but we'll be going through what each of these numbers mean. So first, let's go through PRM. So if you recall, Seabird will select the top K candidate words to replace or insert. So PRM is known as fluent score, which is essentially just the conditional quality of the word toast. That's missing as well. Then next is PRT, which calls Seabird will generate case answers, which will then be used to compute K image text generation. So each of these sentences will be used to take the sentence and the image and combine it together, put it together. In other words, use consent sequence and the sequence as well. Okay, so finally we come to C, which from the very beginning, data will use script to retrieve and most relevant descriptions in the textual memory. So with the K generated sentences, it will complete something called the memory augmented visual related sequence called So data will use Seabird's text encoder and then compute the average constant similarity against the n relevant descriptions. So basically one sentence and then all the description from the initial retrieval. So yeah, so how does it perform? Okay, so it's actually that's pretty well. So what you see here, MSO and figure 30 is the assets, and then your P4 and S is your various evaluation matrices. And if you look at the first row, it's in domain, so basically means that it's trained on the same data set and it's not on the same data set. And then the second one is cross domain, so it's trained on one data set and it's tested on the second data set. And yeah, that comes to the end of my presentation. So I'll pass on to Qianbo. But do you have any questions?
Let's just thank our speaker.
M at 4 is below, if I'm correct. M is meter, C. I don't recall C.
Okay, one slide should be picking up.
So it's P and N is below, M is meter, C is cider, and S is spice. And honestly, I couldn't really understand what it is, but I only know that this is what it means. Export. Yeah, so I'm very sorry, but
Why don't we go and look at that paper and try to down a bit. So if you open up the paper on the metrics, which is mentioned on page 6. It says, and I'll just capture this block of text and dump it in our Slack channel. Again, Shinpen has been quite busy putting nice things for us to discuss. Okay, so can you go back to that thing? Okay. So Blue and Meteor and Cider, they're all metrics for measuring the commonality between ground truth text as well as something that's generated. So these are all machine translation metrics. Okay, blue at 4 is measuring n-gram overlap. Okay, that means the number of tokens that are in the natural language tokens that are in the text versus the generated text. So the more commonality they have, the higher the score. There's some penalty for brevity in blue, because, for example, if you said there's a couch in the image, and another caption that just says couch, 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 couch. And if the ground truth has the word couch anywhere in it, the second caption will get complete 1, right? Because couch is in the caption and it doesn't matter how many times it occurs, right? So there's a problem with that type of metric, because you need to actually form a lucid sentence. So that's one understanding for me. Meteor and comet are more contextualized, so they're not as literal as an n-gram score like me. They tell similar stories. The S metric is the spice. I'm not actually sure what is spice, so it's a semantic propositional image caption evaluation. So it's specifically for image captions, right? So you can also look that up. Won't take very long. So you have a couple minutes to look up the reference. It's number 2 in the proceedings of this paper. You can write it out on Slack. I will investigate it while we go over the next. But aside from that, again, Shinten has asked 2 other questions, and we don't have that many replies yet, so I'd like to engage with that please. Yeah, does that answer your question? Any other questions? Online? Okay, if not, let's thank our speaker then. Nice to Qianbo. By Qianbo.
So today I'm just going to cover understanding. So how do models understand tabular data? So one such model I want to introduce is TAPAS, which is a transformer, which is a bird-based transformer that are used to pre-train and refine on tabular data. So TAPAS takes in the table text in the right sequence of embeddings associated with each word. And each of the embedding is a summation of the follows. So we have W, which is the embedding for the word itself. The position ID, which is the global position of the word from the very first word of the table. Then you also have the segment ID, which is differentiate between the query and the table data, which is followed by your column index, your row index, and your rank. So this rank, right, it's more of a numerical. It's like a numerical ranking among like column. So maybe a numerical data. It ranks which one is from the biggest to the smallest. So a new model came about called table former and argued that models like TAPAS are vulnerable to row and column ordering. So due to the encoding of row information, column information, and global positioning, it introduces row and column order bias. So as shown on the example on the example at the right, the changing of table order can actually influence the result of TAPAS. Table former aims to make these consistent predictions regardless of the order. Therefore, table former changed the input by removing the column and row order information. And since they introduced the bias, they changed the position encoding token to become a per cell position encoding where the index is reset at the start of each table cell. So the rest remains the same. So due to the missing row, column, and global position information, there is a missing element to encode the row relations and column relations among the table data. This was resolved using 13 extension biases that represented 13 table text structural bias and these are the biases. So this is actually the overall structure of the table format. So on the bottom, you actually see how the embeddings are positioned. Yeah, and inside each of the transformers, the colors actually represent like between two columns, like between two like columns, let's say columns or row lah. Sorry, between each element, right? Among them, how do they associate? Whether is it same row, same column, in terms of their bias. So table format actually uses two evaluation data set. So you have your for table question and answering, you have your sequential question answer. And for table text entailment, which is for fact checking, so we have a table fact, fact. And lastly, they created a perturbation evaluation set based on the previous two data sets to check for row ordering biases. So for the evaluation of the perturbation on table format, it uses a metric term variation percentage, which measures the number of answers that change from correct to wrong and wrong to correct out of all the queries. So referring to the result table, right, you see that table format actually shows a strong resilience against table perturbation with a sub 1% change in the BP metrics compared to type R's. So as for the evaluation and accuracy of performance, so evaluated using type fact data set, it shows that table format is actually able to capture and retain information much better compared to type R's, even without perturbation. So now we have understand tables, but how do we understand documents in general? So documents actually have varying layouts and a mixture of text, images, and tables. So how can a document be processed where its layout and content is both captured meaningfully? So today I want to introduce a method which assumes that the document has been passed through a general purpose passing tool. Yeah. So either an OCR or in this case it uses an in-house passing tool. Yeah. That's shown on the right. So in-house passing. So as you can see, they extracted out all the block and extracted all the information such as block boundaries between the bounding blocks for each of the different type of elements. Yeah. So the type of information of the block also represents, it could be like headers, could be headers, paragraph, images, lists, or tables. And the properties of the blocks, of the text in the block, so it's also characterized such as font size, whether it's bolded, italicized, or underlined. And lastly, it captures whether the block contains images. So Lambent does a hierarchy layout on capturing on two levels, the macro block level, as well as the micro block content level. Yeah. So on the macro block level, the content block is sorted by their y-coordinate primarily and x-coordinate or tie-breaking. This is to capture the spatial structure of the layout. Yeah. As thus this is actually results in a zigzag pattern shown on the right. And on a per block level, inside each content, special token use CLS is added to signify the starting of the block boundary. And the rest of the block follows the original order given from the parser. Thus, as a whole, this forms the whole sequence input for Lambent. Okay. So as for the individual tokens, it's actually again a summarization of several embeddings, such as the word piece tokenizer, the index of the content block associated within the token, the type of content of the block, the type of content of the token, and the modality of the token, if it's an image or a text, and the textual features of the token. So aside from the text encoding in the previous slide, the image fed through is fed through a CNN and encoded using a transformer NLP for visual embedding. So this is actually the overview of Lambent, and you can see it's actually split into the two distinct transformer levels. So the lower level is actually responsible for capturing the semantics in the content, while the higher level is actually responsible for capturing the semantics among the content blocks in relation to a layout. So Leopard actually has 5 total like pre-training objectives, split into 3 high levels and 2 low levels. The high level objectives are performed on the content block level, whereas the low level is performed on the content. So the first low level objective is a mask language modeling, which follows Bird's method of masking text and asking the model to fill in the middle. The second low level objective is image text matching, where some of the images in the document is swapped out with an image from other documents, and the model has to detect if the image match with the surrounding text. So onto the high level objectives. The first high level objective is block ordering prediction, where 2 random children blocks are actually swapped, and the model has to detect if and predict if the content blocks are in the correct order. The second high order objective is the image fitting, where some of the images are masked, and the model has to choose the best fit among the candidate images. Lastly, the third high level objective is block NLM. Again, similar to the previous objective, some of the textual blocks are masked, and the model has to pick the best fit given all the textual blocks options. So in order to support the 5 objectives, Leopard actually uses the above loss function, where it's a linear combination of the cross attribute losses for each of the objective. And the lambda weightings are tunable hyperparameters to adjust the significance of each loss. So Leopard is actually evaluated using 2 tasks. The first task is a text block filling task, which involves the model to predict the mask content block with a subset of the remaining content blocks, with the true content block in the subset, given all the prior blocks before the mask content is context. The second task is image suggestion block, where a document is passed in with a masked image block, and the model has to predict the image given with a given set of candidate images. As for metrics, Leopard uses mean reciprocal rank, which is the rank where the rank refers to the rank of the ground truth items among the predictions. So MMR in this case is like the average MMR across all tests. Yeah. Whereas for recall and K metrics, it counts the number of ground truth in the top K predictions. In this case, it counts the number of times the correct block appears in the top 5 predictions of the total number of tests left. So referring to the result table, it shows that Leopard is comparable to other models such as LLM in text block filling, while it also excels at associating the correct images with the surrounding text. With that, let's pass it to Sahej.
Yeah, let's thank our speaker.
This is a question to you, right? Because I think it's actually more like my doubts as well. Right? So when we talk about the whole embeddings of presentation is about surroundings. If we talk about the table data, right? The surrounding has meaningless.
Oh yeah,
Because the column and the row is pretty random. I can combine anyway, still the same table contents, right? So I'm just a little bit struggling to understand how do we embed into the table for tabular data because for database stuff.
Okay, so there are a couple things here. I mean, if you look at the Lambert paper, for example, they have some examples of tables that actually need this type of understanding. So it's somewhat in contrast to what John thinks. So like exactly this table here. Okay? So you can see that there are some columns here that are right. So if you took like the third column and exchanged it with the first column, there are some things that conventionally wouldn't make sense, right? Because we expect the leftmost column to be sort of like an axis thing, right? So when we see method in the top top left corner, and we see that there are horizontal things, then we think the things under methods are rows that are specifying a tuple, right? So you couldn't exchange, let's say, the method with, like, say, the F1 score, which is the third column, right? That wouldn't make sense. Like, we would have a hard time parsing it, right? So there are some things that you can expect from having contextual information useful, right? And again, here you can also tell, like, there's a header that's two rows long, right? First and the second row are actually the header, right? Because see, there's some common bricks like the modality and the method that are localized and on the left side, right? So there is some use in that. It's not that we can't permit. There's actually quite a lot of semantic understanding dependencies that we impose on our understanding of tables.
I see that because when we design these tables here, we actually already putting some semantic inside, right?
Oh yeah.
Yeah, so maybe expanding from here, we talk about database table, for example, which is not so much of semantic design. That is very much a technical thing. In that sense, would that be similar or totally different problems?
So they're similar but different, right? So database tables don't have an inherent serialization into a physical form,
Yes.
right?
Right.
They have a semantic representation. So if you take database, you know about normal form, foreign keys, primary keys, right? And those keys, you can imagine they're the left-hand side, right? But left-hand side is English tables, by the way. If you're doing like Hebrew or Arabic tables, they're right? So there's other impositions that even in Qianbo slides, you will see that the authors in some of the pages have actually imposed their own understanding of the language or the type of data that's being shown. Okay, can you go back a couple pages? Yeah, no, the next one. Yeah, okay, so you look at the figure here, and maybe there's another figure where there's the zigzag.
Oh, yeah.
Okay, so this zigzag, if you just look at this one, you can tell this is an English document, right? And you can tell it's meant to be read from right to left, then to the next line. Because you look at the rows are contiguous. The blocks are only changed at a row level. You can clearly see there's one row, then another row. It's not two columns, right? Because the columns don't line up, right? But in some newspapers, they do line up, and you're meant to read vertically, then horizontally. Yeah. Okay. So there are other types of nuances that when we do layout information, we take into account. Okay. So there's another set of works that we didn't go over today. When we do the hierarchical level, we try to look for the maximum dividing lines first. So if you can scan, like say, look at this picture here, where there's 5 green blocks, say, what are the vertical and the largest vertical or horizontal lines that you can make? Okay, you can see here, there's 2 horizontal lines you can make. One between 1 and 2, 3 and whatever, and one where the ellipsis is, right? And that breaks the thing up into 3 regions, right? Then you can recurse on this and say, within each of these blocks, what's the maximum dividing line that I can make in each of these, right? And you can see I can split 1 from 2. And then maybe even the 1 block, you could make other lines, right? And in English, that's very possible because each line, usually there's a white segment that you can draw all the way across, right? But in certain other languages, like for example, in traditional Chinese, it can be written up and down, then you would see other lines, right? So there's many different ways that we can impose our understanding, our biases, our priors into a document understanding system. Okay, our groups have done this, my group, and some of our PhD students that work on these problems. Okay, but to come back to Jonathan's point, yes, tables in database table, they're logically the same, but when you serialize them, they're very different, right? When you want to take a table in a database and put it on the screen, you tend to put the keys on the left-hand side if you're writing in an English document system. Does that help?
Yeah.
Okay. There are other contiguities as well. If you go back to the other, let's say the result table that we were looking at, okay? Like even from far away, imagine you're zooming out, you can't even read it because you're at the optometrist's office, okay? Then you would know that certain things are numbers, right? Because they collide and there's like a decimal. And you know that certain things are bolded, so there must be important in some, right? So those types of pieces of information, again, when we do table processing, we usually take into account. Okay. For example, font size is meaningful usually only because it's relatively different between other font sizes, right? So you can't say, 12 points is big because it depends on what the other font sizes are, right? If you're on a poster, that's tiny. But if you're on a 3x5 card, that's huge, right? So you need to know those relative differences. Okay. So if you don't notice these things, it's because you don't look at a diversity of input, right? Because you think, oh, all my tables look like these, so that's have a natural position, right? But you can think about in other domains, right? Like you can think of like in medical documents, in financial transaction statements, in newspapers, anywhere there's tabular information, like on baseball cards, all of those things, they're different presentations. So for a language model to do well, it means that you have to know the domain of information. So when you read these papers again, try to take a grain of salt. Other questions? That's I'm sorry, I tend to do this like ramble. Any other questions? Okay, I wanted to go back to one of the other earlier papers you had on table understanding of table former. So table former, if you look at the tuning, it's the one after this. No, one more after that. Like when you go to the loss function. One more, four, when you have all the lambdas.
Oh, lambdas is lambdas is the that.
Okay, can you go to that one? Okay, I want you to guys stare at this thing for a second. Do you know what this means? Okay, when I read this as an expert, it tells me something. It tells me they have no idea what's important. Okay, why do I say that? Can you tell me?
They don't have dates.
They don't have dates.
Dates for like
Weights.
each of the parameters.
Right, the weights are right there, right? They're the lambdas, lambda 1 through lambda 5. Okay, so that means they're letting the data speak, right? They're not putting any priors. Say we have no idea what's important, so we'll let the machine decide. Okay,
So it says it's hyperparameter.
yes, they're hyperparameters. Okay, so that means the paper actually did set them. If you go to the paper, they will have told you what they decide. Hyperparameters usually means that they're too expensive to set by machine learning, right? So you have to give them some initial value. Okay, so I would like you to think about this. Okay, if you know what all these things mean, MLM, ITM, B or B, MLM, image fit. Okay, as a computer scientist, either undergraduate or graduate, I would like you to guess what these parameters should be. If you can guess what the the components actually are measured as. Okay, it's a very important point when you train to be a scientist. Okay, is that you have to have your own hypothesis for why these are fit the way they are. Okay, because run machine learning, it will give you the coefficients, but you have no idea whether the coefficients it's found are good or not. They're good for optimizing against your task, but you don't know whether they represent the reality that you want. Okay, because that happens a lot in machine learning. Like the systems will optimize the mathematics, and they're not actually optimizing for what you think you want to optimize. Okay, like you've heard of spurious features, maybe spurious correlations, right? Or machine learning models that have subverted what the designer wanted to do. It's because they found some shortcut to get, right? And so that happens a lot if you don't have intuition. Okay, you should definitely do this, but you should have a hypothesis before you execute your experiments. Meaning that, for example, oh, because my data has no words in it, it's all, for example, natural images. Okay, then I think the MLM one is useless because that one's for words, right? But if I'm looking at newspaper articles, like this paper had tables from newspapers, that should be a fairly good source. So I think that that parameter should be set high. Okay, but again, as scientists, as people training, you have to have a hypothesis for how you're going to set these parameters on your own and run the experiment and tell us whether your intuition matched what the computer found. If it doesn't, you better go back and figure out why it doesn't. Because if you don't, you're letting the algorithm dictate your work, right? I mean, why do I need you? Just let the model decide. Okay, so that's really important. You have to have locus of control. You have to have an envisioning of what's going on. In a lot of cases like this, when, for example, the losses here may not all be 0 to 1. If that's not the case, then these aren't comparable with each other. That's a huge problem in normalization, because usually you want these things to be unit losses, right, between 1 and 0, so that the coefficients sort of make sense. They should add to 1, right? Because if they're not, then you can't make any sense out of whether lambda 1 or lambda 2 is equal. So make sure we're clear. Can we go back to the two former paper, table form? Okay, so another thing I would like you guys to emphasize is don't worry too much about the results. Okay, because the results, they won't tell you a lot. They'll just say every paper says the same thing. One paper is better, our paper is better than the baseline, right? Because otherwise you can't. That is so super worthless. Okay, so concentrate more on what you think is the key idea coming out of the paper, right? So like Qianbo writes on the side, you know, it shows strong resilience against perturbation. So what is the perturbation that's been shown here, and why is that? So those are important things. All right, like I said, I've wasted too much time, so I think let's thank Qianbo.
Before I continue, I'm going to take a toilet break real quick.
Okay, yeah.
Yeah.
Let's take a break. Yeah, we're ahead. So yeah. So we'll come back at 20. Yeah. 20.
So that is a possibility of some other avenues. So
You can propose one. Yeah, anything for the proposed lab is supposed to be done. You know, typically problems are but sorry, combine with some of our lab object. So each that's why we have some other reason are to take the right issue so the education
Was mine.
sorry. Sure, I mean, there are rough interest areas. All right, so it is 20 past, so I think we'll get started again. So thanks for reminding me we need it, but that's great. So yeah, Zaidan, you can take it away.
Right, so now I'll be covering a bit about chunking. So I'd like to start a bit with a more practical view in terms of tutorial. So basically when I started doing RAG, how I did first I didn't understand what chunking was. So there's a general quick one is what is chunking? Chunking is the breaking down of large documents into smaller pieces for more efficient information retrieval. And if some of you may not really may know how to use chunkers, but may have not seen like a visual representation of the differences. I thought this tool was pretty useful. It has slang chains, recursive character text splitter, as well as like the different document or OS separators. So if you want to look at that and see how it looks like, I think that's a pretty good visualization. And then if you take a more practical look, this was a tutorial that I used when I first started. It was the 5 level of text splitting. Basically, if you know the experimental semantic chunker within LangChain, that was implemented based on this tutorial. So yeah, that's a quick understanding of what are a few ways to split text. We have by a fixed length, by a series of separators, so meaning your new lines, etc., etc. Document specific, where you take into consideration keywords in maybe code languages like Markdown or specifically like Python or JavaScript, like your function code words. Using embeddings, which is semantic splitting as well as agented, so you use an LLM and pass it to help you chunk. So roughly these are some practical ways, but looking at some papers that are interesting for this for chunking, some questions that you might ask is how do we split chunks based on intent? Because we know that we can split chunks by length, by maybe similarity, but a lot of times you want to chunk based on the question that you ask. So is there a way for us to split chunks based on intent? So that will be covered by the first paper. The second paper is actually related to a question from the audience in the previous lecture about granularity. So how do we choose what is the best granularity of a chunk? And then this method here actually looks at a way to do that within the model. Next is a very quick technical report of how to evaluate chunking strategies for retrieval. So I thought this would be interesting because for some of the projects, you all might want to evaluate this. So this might be useful. And lastly, it's a bit of a real world look at whether semantic chunking is actually superior. We see results that show that semantic chunking is better, but is it actually better, or as what Prof said, is it really like in real life situation when we are actually using it for our real implementation, is it actually better? So I'll first begin with the first paper, which is pseudo instructions for document chunking. So when a user inputs an instruction, so maybe like a query, right, we want to ensure that sentences relevant to the instruction are grouped within the same chunks, while unrelated sentences are placed in other chunks. Basically, we want some form of locality where like the chunks are like the terms that are important, the context important are close in proximity. And you want unrelated sentences to be placed in other chunks. So, but then the thing is, when you make a system like this, how do you predefine chunks based on specific instructions, right? So this issue, what they do here is we get pseudo instructions. So what are these pseudo instructions? They are actually the document summaries. So this preserves like key document information. So these are in this paper it's generated with LLMs. They generate the document summaries. And then they basically compute semantic similarity scores between each sentence and the summary, and then they group sentences with scores above and below the average similarity threshold. So in general, the pipeline is that basically each summary has each document generates has a summary generated, and then and then first you have your original most granular unit here, which is sentences, and then you just you get the embeddings, and then you do a similarity search, and you dynamically group adjacent sentences chunks. So if you look at the math, it's relatively simpler than the stuff that you've seen here. It's just a similarity, cosine similarity at the top between the sentence embedding and summary embedding, and then the things below are the chunking rules, where you look at where all the relevant chunks are basically just chunks where the sentence before and after it are considered irrelevant, and the ones within it are considered relevant, and vice versa. It is like a on-off switch if you think about it. If you look at the diagram here, so it's like a kind of a Boolean, not Boolean, right? Like a green red or green red green red green. And then the threshold is the mean similarity mu between all sentences in document D and summary. And the paper does cover a bit about the consideration made for this threshold later. And I'll explain that in the first slide. So just a quick look at the performance as per normal, good, bad. Yeah, so these are the results. Another thing that they did do, which I found quite interesting, was that they tried to like understand the importance of pseudo instruction implementation. So if you remember, the pseudo instruction here is actually the summary of the document, right? So they for this to do the pseudo instruction, they tried other things to see where if this actually mattered. So they use a random summary of another document, or just pick a random sentence within the document and pick and use it as the embedding. And another one is they pick an average embedding. So from this, they find that it is important to a certain extent what the pseudo instruction chosen is. Random and generally the worst because it's not related, unable to pick up the semantic similarity stuff. And yeah, so this is like the comparison between other pseudo instruction implementations. And with regards to the threshold in terms of similarity, whether it's irrelevant or relevant, this is their graph to show the influence of different chunking thresholds. However, I think, at least for my personal opinion, it feels like when I'm looking at this paper, they are not. It is still within consideration. I think I think you have to look into more depth to understand what would be an appropriate threshold for this kind of. So we remember that PIC uses LLMs to generate the summaries for the pseudo instruction. So there is again added computational overhead. So it depends whether it is it depends on the cost of the LLM, because now you have an extra step in your pipeline where you have to generate extra stuff. And then in addition, current evaluation that they did was limited to general domain tasks. So this might not work as well for specialized scenarios requiring cross documentation. In addition, they also took a look at when the real instructions are known. In this case, the real instruction that they chose was a dataset of anonymized queries. And they find that it would be better to use it if that was possible. So if that is available, then that might be better. So yeah. So that was it for PIC, pseudo instruction for accounting. So from last week, someone asked a question like, what granularity should we use for the different kind of queries like coarse and fine queries? So this question is answered by this motivates the idea of a mixture of granularity. So we know that so there has been a lot of surveys on what is the optimal chunk size if you're using like a length-based splitter. And if you look at the RAD survey papers, you'll find those. So you know that optimized chunk size is essential. However, we also know that not all data stores are built similar. So like not all databases are built similarly. So you have different optimal chunk size. And then if you use uniform chunking size for all queries, it might yield suboptimal retrieval because different queries have different granularity, right? So if you look at these kinds of questions, as you see the first question, it's a bit it's very fine grained, so it might need a bit more information. And for the second question, it's a bit more broader. So in a sense, different granularity might be required for different questions. So maybe a quick question. Any of you familiar with mixture of experts? Maybe anyone want to try explaining?
Anyone want to explain? Yeah, okay.
Yeah, it's like a model where you train smaller models. So inside the model, there are smaller circuits in a way, and they all are trained on different features. So it's like one circuit becomes an expert of something, and so on.
So what you said is pretty much what it is. It's basically like you train specific expert models for specific subtasks. It's similar to this. You train you have different granularity and they are used for different subtasks. So that is the motivation for this method. So how does it work is that basically the corpus is chunked with a set amount of granularities. So and then when queried, the K most relevant snippets are extracted. And that is the selection strategy. Basically, you select the top K finals being chunk and then you retrieve the chunk containing that from the optimal granularity level. Okay. So basically, this is a general diagram of how it works. As you can see, the query, you can put it in embedding, and it goes through the module and it finds out the snippets selected. It does the selection strategy. And yeah, so yeah, it's a bit confusing. What I understand from this selection strategy is that it has weights for each it tries to find out how important granularity is. So it has a weight for how important the granularity is to that query, and then it uses that to decide which granularity to use. So there's a bit more nuance behind this diagram that isn't really shown. So that's how the selection strategy works. It basically takes in and it uses like the module to determine a certain weight of like what is the importance of the granularity to that, and then it applies that weighted score as well as the semantic similarity. So a question might be, why not just take the chunk that has the most semantic similarity out of all the granularity? That might not work because the bigger chunks will generally always have higher semantic similarity because they will contain more keywords. At least that's what they propose. Therefore, we can't use like just to take the best semantic similarity out of all the chunks there. Yeah. So, but if you look at this, there was like a different acronym here that used MOG. So they say that naive MG works when adjacent snippets with relevant knowledge can be retrieved together. What if you are working with questions that require cross-document reasoning? So like information from two different documents. They propose a graph-based representation where the granularity level is changed into the hopping range. So links are added between your nodes inside your chunks basically if they hit the semantic similarity threshold, and then basically it's and then basically the amount of the clarity is basically the amount of hops, and then it's the same process in terms of deciding what's the granularity and then retrieving the correct one. So basically this was this paper specifically looked at medical data sets. So the results here are based on comparisons with basic retrieval augmented system made for medical purposes as well as Qianbo. So the limitations that they say that the method has is that there is an added security risk because now you have more components inside your pipeline. You'll always add a new security risk, so you need to protect the MOG router, and also that the granularity levels that they mentioned are actually not there's no like automatic setting. It's like they chose the granularity level themselves. So in this case, I think they chose 5. So they was that there needs to be some algorithmic way to set these granularity levels. So those are like the two main papers I wanted to cover. Next we have just a quick paper. This is not really a research paper, it's a technical report from I forgot which company, but basically these are just some metrics that could be useful for evaluating chunking strategies. So we are familiar with the precision and recall metrics. There's also this IOU metric, which is basically to take into account whether the relevant search are retrieved and how many relevance are also retrieved. So this could be a useful scoring metric if you want to use it. Yeah. So lastly, I wanted to end off on a bit of something that I thought was quite interesting in terms of, because naturally you would think that semantic chunking would be better than fixed chunking because of the way that it's. So so for this paper specifically, it runs a few experiments on semantic chunking and fixed size chunking on view datasets. So basically they compare fixed size, quick point, and clustering. So quick point basically when you do semantic chunking, you find instead of you basically look through to find breaks, break points, find points that you can break into chunks. And for clustering, it's you take sentences and then you use algorithms to cluster together. So the final ending point that I wanted to end on is that some although synthetic datasets may show certain results, real life datasets show better performance without it. So I thought a very interesting part of this was that it says that it suggests that in real life the topics in the document may not be as diverse as it artificially noisy and so in this case, a possible future look at what chunking this consider is that the synthetic datasets really good measurements for to measure these chunking mechanisms, or is chunking really is semantic chunking really necessary considering that if your real dataset doesn't have the issue of splitting the topics in the document all around the field. Okay. So I thought this was an interesting question to ask, and maybe since we have a bit of time, I'd like to open the floor to any of you that have a bit for since I'm actively done in my presentation. Thank you.
Let's thank Zaidan. Well, he ended with a question, right? Right there. Are synthetic data sets realistic measurements?
Yeah, so like I think okay, I didn't type for that, but is it realistic to use them as ways to evaluate? Because that is like what we compare these chunking mechanisms to, right? That's how we test these chunking mechanisms. We say that, oh, this is good because in blocks we have this does well in this metric, this does well in that. But if it doesn't translate to real life performance.
Okay, do we have any answers people want to say either online or if you're online, you can just unmute. Or maybe locally here, anyone wants to try to answer this question?
Just clarifying, what's the real life data set that they were using?
So let me just if you want to look at it, I already forgot, but
Because the paper,
Yeah, so-
yeah, you're
there's no- So these are these are the data sets in the appendix. So Casper here was covered in one of the other papers. It was covered in PIC. It's basically, I believe, something to do with it has anonymized queries from like a Google query set. I believe that was what it was used for in PIC. Yeah. Yeah, these are the different types of data. So
So what do you guys think?
maybe a different way to look at it is if this implies that we can't really trust synthetic data sets, then is there any way that we can try to evaluate this? Because it does mention in the limitation of this paper that there is a limit to how many data sets are actually available to actually train on, and that's why we have
Okay, so this is supposed to be a bit of a participatory class, so I'd like to just poll you guys who thinks Zaidan's question, is it possible that we use, I think you said synthetic data to evaluate appropriate, right? Is that what you asked? And we just have a poll of hands who thinks it's appropriate? Yes. Who thinks it's not? Who thinks this is a trick question? Okay, if it's a trick question, what was the trick? Yeah,
I'm not really sure, but I've seen okay, I've heard of a paper that said that if you generate synthetic data to train the model, and then let's say you've trained the model, then you ask that model to generate synthetic data, and then you repeat this, the model will eventually the responses will become like rotten in a way. They'll be unsent. They won't make any sense.
Okay, so the graduate students, you know what this is called? The model collapse.
Yeah, model collapse. Yeah.
Model collapse. Okay, so this happens a lot because the system's logic start to get much more peaky, right? But originally they're not very sure, but as the model trains again on those strings that it's good at, and it starts to generate those strings that it's good at, it gets more and more confident that it knows what it's doing, and it can collapse, right? So that the distribution becomes very peaky. So you see zeros everywhere, and then 1.0. And it's going to generate those data points that look like that. And so it's reinforcing stuff, right? So exactly like what Wei said, this happens a lot. So we tend not to train on things that we test on, right? I mean, like giving yourself practice paper where you've just done it like 10 minutes ago, right? I mean, you just memorize. Okay. But is it, I mean, what other problems do you see with this question that we posed just?
Like there's another issue to be raised with integrity of like scientific integrity as well. Because if you like cherry pick the prompt that you use to generate your own synthetic evaluation data, so you can just pick one until you get good results for your own method.
Okay, in fact, that's what we normally do. Picking things that we're good at is called optimization. And that is machine learning. So we're trying to optimize, right? So there is another problem that Ada didn't mention that I want to point out is that somehow the question that we're asking is not very well formed, because even if we say create data, synthetic data, the question is how are you creating that synthetic data, not whether you're doing it or not, right? If you're creating the synthetic data that is a genuine close representation to the target distribution, and it is not model collapse because you're not training back on the same method that you're generating, then it could be a good representation. Okay. But simply saying that you're using synthetic data or not using it doesn't answer the question about whether it's good for you or not. Okay, does that make sense? So it's sort of like an orthogonal question. Okay, many times we associate synthetic data with low quality stuff. Okay, and so you would say, it's like junk food. You eat a lot of junk food, you're going to get fat, right? So you're not going to be a fit model in that sense, right? But you can think of it the other way. If I don't have any food at all, I have sparse data, then McDonald's is perfectly fine. Okay, I'm sorry, McDonald's, I didn't put you on. You do. But the whole point is like junk food is still food, right? So you can use food for some purpose, right? But if you have some other more holistic food, maybe then it might be better. So you have real data that's close to the target testing data that you want, then of course you want to use that, right? But in many cases, we use synthetic data that's much more diverse because we want it to be robust. Okay. There were some cases, even in the earlier presentation by Qianbo and also by Zaidan, that there were certain model interventions that people did to make the models more robust. Can anyone name any of those things that people did? Make the models more robust to noise or failure? There's a couple slides now. You go back. Okay, right. Yeah. Well, what are we doing to make the model robust in this spot? Don't all shout at once, okay? It's so noisy. in the room. Okay, Zaidan brought up mixture of experts. Okay, why is a mixture of experts something that makes it more robust?
Because is it because like the experts are like catering to different things, and the more orthogonal like something is, the more like aspects you cover, so you can get a view of the same thing from like different perspectives.
So Intra made a very good point. Okay, is that when you have a mixture of expert, each expert is getting trained on different pieces of information, right? So we tend to call that in machine learning feature projection. Okay, if you know what features are, right? So in machine learning, we have this idea that there's a vector x. It's composed of multiple things, right? X1 through Xn. And these are all different features, like they're different columns, right? When we do feature projection, we're basically saying that we don't want you to see every piece of information. We're going to hide some pieces. Maybe I give one learner X1 through 5. I give a next learner 6 through 10. I give another learner 11 through 15. Okay. The free learners are just going to have those 5 features. They're going to learn their own idea. And then we're going to ensemble them together in a mixture, right? So we say mixture, it's the same as a Gaussian mixture or anything like that. Mixture means we take several models and we compose their information together. Okay? So if you heard of a Gaussian mixture model or ensembling, those are all these strategies where we say, we don't know what we're doing, but we're going to take votes from everyone. So it's like crowdsourcing, right? Put all of these together to get a decision, right? But so it's like in many cases, it's like all of us in this room. We might be hearing the same lecture, but we came from different backgrounds. Therefore, we have different biases when we're trying to learn this material. So I might do better in asking all of us, ask the audience type of question and getting a response from crowdsourcing, right? So that's what we mean by mixture of experts. So that makes it more robust because each expert could be wrong on its own, but in aggregate, we get better results. Okay. There's another one that we've heard of earlier, okay, masking. We all know what masking is. And I think another person also mentioned dropout. I think Jonathan mentioned dropout. Are all of us familiar with what masking and dropout mean? Yes? Can someone tell me? Because you guys are nodding yes, right? So don't be shy. We're nodding yes. Yeah, I know. Okay. So recognizing it is different from producing an answer. So produce an answer for me. So, and
I guess dropout is like turning off some of the neurons in the neural net just so that I guess the training is generalizable to the rest of the neural net as well.
Right. Okay. It's basically saying I'm going to handicap you on purpose. I want you to learn anyways. Right. So like for example, a robot has lost vision in one eye. Can you still function? Or you've lost a limb. Can you still function? Right? Or more commonly, your input sensors are miscalibrated. Like you see this all the time on Google Maps. Like I'm not actually there. I'm somewhere in this circle, right? So it's not calibrated very well. Okay, but I still need to learn from that. I still need to produce a recommendation for hamburger restaurants in this area, right? For example. Okay, so that's exactly like what Ben said for dropout. Okay. What about masking? What's masking?
Like, I mean, the early remember is actually you cover some word and actually you train that model instead of showing errors.
Right. So we do that in all the word embedding models, right? We mask things out and we say, oh, can you guess what was there? Or can you still make an answer even though you can't see those words, right? They're all forms of feature projection. Okay. So who of you know about decision trees? Everyone knows decision trees? Okay. Do you know a model that's robust in decision trees? And what is it called? Random forest, right? So what's random forest? It's also a projection model. Okay, it's the same idea. If I had, again, 15 different features and each forest or each tree learning model only gets 5. Okay, that is basically random forest. It's saying that I'm going to give all the features to the learner, but the learner is just going to make a whole bunch of trees where I cut off certain parts of the feature space and then it has to learn. Okay, so I use this forest and I combine all those forests together in an ensemble. That is a random forest. Okay, so this idea of making things robust by either masking things out or dropping them away, doing feature projection or instance projection, which is the other one, which is like I have a data set of 5,000 points. I only learn one model with 1,000. I learn another model with another 1,000, and then learn another model with 1,000. That's another way to do projection. Okay, so generally you can say I have this big, table that's R rows and C columns. Okay, and I can sparsify it anyways. I can take a machine gun and shoot parts of the table out. I could cut off rows. I could cut off columns. All of that is to produce separate surrogate models that you can then ensemble together. Make sure when you have missing data, you can get.
Oh,
Yes.
Can I ask a question about masking?
Masking.
So like when you mask, you're essentially creating more data or old data, right? Then wouldn't that kind of also bias logics and kind of like cause model collapse? Or is it like completely different?
It can lead to that if you're oversampling. Yeah, if you create too many instances from the same data, then you're repeating itself, right? So you have to do it in the right proportion. Sometimes the proportion matters a lot on the density of your original data, right? If you have a lot of good data to start with, you usually don't need to do augmentation, because whenever you do augmentation by doing masking, you create more data, but if your models are already well trained, then you start to get model collapse. Okay, but if you don't have a lot of data to start with, and you don't have enough data to set the parameter as well, then oftentimes we do some type of augmentation. Okay, so these are things that in many papers you won't see specifically. You have to sort of generalize all the things that you see, right? So when they do augmentation, you need to think about how much was the original data? How clean was that data? When the augmentation is taking place, how much does the augmentation relate to the original data? Okay, how big is the model size? Because if the model is very complicated, you need a lot of data to set parameters. Okay, if you're doing something like linear regression, easy. Okay, don't need a lot of data. Probably don't need to augment. Does that make sense?
And
Other questions? Tao, do you have any comments from online?
Oh, hi, thank you very much. Okay, I mean, some quick comments are that first, I think today's contents are quite complementary in the context of RAG. As I mentioned in the Slack channel, I mean, right now, every day, both Google and ChatGPT are receiving billions of inputs, either queries or prompts. That means one size does not fit all. That means for different queries or prompts, I mean the user information needs behind these inputs are will vary a lot. That means there will be some queries that need to perform like a table-based multi-hop and reasoning or understanding. Therefore we need this like a table former, like this kind of style specific methods. That means these complementary methods should be combined or used in different cases. This also echoes our previously mentioned concept called like adaptive or dynamic retrieval according to the properties of input queries or prompts. That's one thing. Another thing is today we discussed about document representation. I'd like to say that in the context of RAG, the way we use or we select the method for document representation, to some extent, it determines how we inject the retrieval for augmentation, like using the raw text or embedding vectors or even parametric way, as I posted last week. So that's the 2 points I'd like to add. Thank you so much.
Those are great points. Okay, that reminds me of one other thing that I wanted to bring up that then I'll be quiet. So, is that a lot of what we're learning now actually has many roots from previous work in IR. So when Zaidan went over chunking strategies, okay, mentioning the hierarchical information. Actually, several hierarchical information has been done for a very long time because of XML retrieval. Okay, XML, as you probably know, is like HTML. It has structure, so there are parent cells that have recursive smaller cells. So you can think of a document having an H1 and then a body tag, which might have multiple paragraphs. Inside the paragraphs there are spans that are bold. So they create like a tree-like structure of a document, right? And to do those types of evaluation of XML also requires things like precision and recall over different chunks, right? So here you have the intersectional reunion, which helps you measure like how appropriately sized chunk you retrieve, right? Because if you have a very large union and a very small intersection, that means you didn't retrieve very well. But if it's close to 1/1, then we have done a good job of coming up with the right granularity of retrieval. Okay, there are other similar metrics for windowing. So when you're thinking about segmentation or chunking, and it's just from 1 to n rather than hierarchical, there are other metrics that we use for that. So you can imagine, for example, how you would do that. I mean, you would want to get a segment that starts at beginning and ends at n, but what happens if you make it too small, too big, or it's misaligned? Like you start earlier than it's supposed to start, or end earlier when it's supposed to end. So there's some overlap. Okay, so there are metrics for those as well. Okay, so there's a lot of cases of that. Jonathan, yeah.
So intersection of union is very much used in metrics in the computer vision here. So in the large language here, I'm successful to define model.
Yeah, we use similarity as well.
So this seems like similarity.
This is the similarity of items in a hierarchical space, right? But here, this one doesn't take into any account of the semantics of what's being retrieved, right? It's just saying that there are units, and I want to know whether I retrieve the right amount of units or not, right? Because we're treating this as a set computation, right? So I don't care about the elements set; they're all just units. Does that make sense?
I think set explained.
Okay. All right, so I think we better stop there because it is already 8 o'clock. So thanks for coming today. Again, I will be manufacturing all of our groups on the STEPS portal. So you should be getting emails from the STEPS portal. Do check your spam email when I tell you to, so I will write a message on the general alcohol. And make sure you get your project script done. Thank you so much. Let's thank all our speakers again.